Our last video clip introduced our atmosphere and also talked about the composition of the atmosphere. This video clip will deal primarily with the vertical structure of the atmosphere, but there's one topic regarding the composition of the atmosphere that I didn't quite fit on the last video clip, and that's comparing our atmosphere to that of other planets. The diagram I used here is an old diagram from NASA. Clearly it's pretty old because Pluto is still shown as a planet, though the link here is up to date, and it links to the updated site with images and information on all the planets of our solar system. I just like this diagram. You might be surprised to learn that the atmospheres of our neighboring planets vary considerably. In fact, Mercury does not even have an atmosphere. Basically, the ability to retain an atmosphere depends on the mass of the planet, thus the gravitational force, and the temperature of the planet. First, let's consider the mass of a planet. As your book mentioned, the gravitational attraction of the Earth is what holds gases close to the Earth's surface, creating the Earth's atmosphere. Notably, the more massive the planet is, the more gravitational force it exerts. Thus, a more massive planet is able to hold on to more atmosphere and thus have a thicker atmosphere. By the same token, a smaller planet is likely to have a thinner atmosphere. Temperature also plays a role. We will learn later that temperature can be defined as the average kinetic energy, or energy of motion, of molecules in a system. At higher temperatures, the molecules move faster, and this energy can help them escape the gravitational pull of a planet. Thus, hotter planets may tend to have thinner atmospheres than cooler planets. Of course, this simple explanation of mass and temperature and how it affects a planet's atmosphere is a simplification of what might be studied in more depth in an astronomy class, but it gives us the foundation for understanding how atmospheres may differ among the planets. Let's look at a couple planets. First, let's consider Mercury. Mercury is small, so it doesn't have much gravitational force to hold an atmosphere. And it's also the closest planet to the Sun, so it has very high temperatures, which allow the gases to be able to escape more easily. So essentially, Mercury has no atmosphere. And as a result of having no atmosphere, it has no mechanism to protect against temperature extremes. You might remember that regulating temperature is one of the most important things about the Earth's atmosphere. Thus, daytime on Mercury is crazy hot, approximately 800 degrees Fahrenheit. And nighttime gets more than a bit chilly. It's approximately negative 250 degrees Fahrenheit. That's over 1,000-degree temperature shift from day to night. Yikes! Next, let's look at Venus. Venus is larger and thus has a thicker atmosphere. And its atmosphere is composed primarily, over 95%, of carbon dioxide. Notably, carbon dioxide is a greenhouse gas. It's very good at absorbing heat. And as a result, Venus is very warm. Even though it is farther away from the Sun than Mercury, the daytime temperatures are hotter on Venus than on Mercury. Also, since the heat is retained due to the high amount of greenhouse gases, particularly carbon dioxide, nighttime temperatures do not differ significantly from the daytime temps. Indeed, the temperature on Venus is always approximately 850 degrees Fahrenheit. Wow! I don't think we'll be moving to Venus anytime soon. All right, you get the idea. You know what the atmosphere is and why it is important. We covered that in the last clip. Also, you know that the atmosphere can change over time, and that atmosphere thickness and composition varies from planet to planet. Now let's return to the Earth's atmosphere, and in particular, let's look at the vertical structure of the Earth's atmosphere. Our atmosphere has different characteristics depending on altitude. Thus, next we're going to look at the vertical structure of our atmosphere. First, we're going to consider the different layers of the atmosphere based on temperature. Then we'll look at how pressure and the composition of our atmosphere vary with altitude as well. So first, how does temperature change as altitude increases? Temperature is not constant throughout the atmosphere. You likely knew that. From your experience, you know that temperature seems to decrease as you go up in elevation. It's tempting to think that temperature might continue to decline forever out into space, but that's not the case. To better understand and study the atmosphere, scientists have divided up the atmosphere into layers based on temperature patterns. As you can see from this diagram, there are 5 layers to our atmosphere based on temperature. The troposphere, which is the lowest layer, extending from the Earth's surface up to 5 to 11 miles above the Earth's surface. This is where we live, and this is the air we breathe. Then above that is the stratosphere. You've been in the stratosphere if you've been on a commercial airplane. It's roughly 11 to 30 miles above the Earth's surface. And this is going to be important in our discussion of ozone depletion. Then there's the mesosphere, up above that, the thermosphere, and the exosphere. In this class, we will deal almost exclusively with the troposphere. Climate, weather, and air pollution are all tropospheric topics. The 2 exceptions to this are our discussion of vertical temperature trends, which we're going to do shortly, and our discussion of stratospheric ozone depletion. So first, let's look at the vertical temperature trends. Study the figure shown here. You can see that the y-axis here is altitude, and the x-axis is temperature. How does temperature change as altitude increases? Notice that in some layers the temperature decreases as altitude increases, but in other layers the temperature increases as altitude increases. Pause the video and check this out. First, let's check out the troposphere. How does temperature change as altitude increases in the troposphere? As you go up in altitude, hopefully you said the temperature decreases. Why is this? Actually, it's pretty simple. The heat source for the troposphere is the Earth's surface. The further you get away from the heat source, the colder it is. It's tempting to think that the sun warms the air around us. That's not true, at least not directly. The sun warms the Earth, and the solid Earth warms the troposphere above it. Next, how does temperature change as altitude increases in the stratosphere? You can see that it's quite different than the troposphere. Hopefully you can see that as you go up in altitude, the temperature in the stratosphere increases. Interesting. What's up with that? The top of the stratosphere has a higher temperature than that closer to the Earth in the stratosphere. Well, the top of the stratosphere also has a higher concentration of ozone than the rest of the atmosphere. And ozone is good at absorbing ultraviolet light from the sun. As that stratospheric ozone absorbs ultraviolet light, it warms the top of the stratosphere. Thus, as you go up in altitude and get closer to the heat source, the ozone in the top of the stratosphere, the air warms. Let's keep going up to the mesosphere. You'll notice that the mesosphere has the same temperature trend as the troposphere. It gets colder as you go up. Why is this? Well, the heat source for the mesosphere is the top of the stratosphere, that warm region where ozone is absorbing ultraviolet radiation. Thus, as you move up and away from the heat source, it gets colder. Moving further up in altitude, for our purposes, we'll assume that temperature continues to increase with altitude in the thermosphere and exosphere due to the intense UV radiation from the sun. However, this isn't really the whole story, as at some point molecules are so sparse that there's no temperature. Temperature is defined as the average kinetic energy of a molecule, so how can you have temperature if there's no molecules? Interestingly, then, space has no temperature, but objects in space can be very hot in the sun or very cold in the shade.